This presentation describes the details of the superheterodyne receiver. A superheterodyne receiver is a selective receiver that can be used for any type of modulation. The basic block diagram of a superheterodyne receiver is shown here. The receiver is designed to receive the AM broadcast band in the 540 to 600 kilohertz range. As shown here, the frequency that we focus on will be the 10 kilohertz station centered at 980 kilohertz. First, we will go through an overview of the system and then step through it more carefully. The AM broadcast band extends from 540 to 1600 kilohertz. Our goal in this example will be to receive the signal at 980 kilohertz that we refer to as FC. The carrier frequency, FC, enters the RF amplifier via the antenna and then actually enters the amplifier. The RF amplifier is a variable tuned amplifier. When a station is tuned in, the center frequency of the tuned amplifier is adjusted to the carrier frequency, FC, by tuning one of the elements, like a capacitor. This allows for maximum gain of the amplifier to be at the carrier frequency. The RF amplifier is not a selective amplifier, so it also passes adjacent channels in addition to FC. This is a potential problem that we will discuss shortly. In the mixer stage, all of the signals passing through the RF amplifier, including FC, mix with the local oscillator signal in the mixer. We know that when two sinusoids mix, or multiply, the product that they produce is two sinusoids at the sum and difference of the original frequencies. Thus we know that the sum, FLO plus FC, and FLO minus FC will result. Based on whether FLO or FC is larger, we will have FLO minus FC or FC minus FLO as the difference frequency. This is indicated with the absolute value signs. The output signals from the mixer with its sum and difference frequencies enters the IF amplifier. The key of the superheterodyne receiver is to set the local oscillator so that the desired frequency at FC is shifted via the mixing process to end up at FIF. The IF amplifier is the component of the receiver that provides selectivity to the receiver. It will only pass the single channel at FIF, or the IF frequency. This is the station that we are trying to receive. Its passband is only 10 kilohertz wide, the bandwidth of the received station. The FC signal can be either shifted to FLO plus FC or FLO minus FC, depending on the design of the receiver. If the IF amplifier has a bandwidth of 10 kilohertz, the same as that of the received AM station, then it will be the only signal to pass through the IF amplifier and into the demodulator, and hence the only one signal that is demodulated. The fixed IF frequency is used because it is more feasible to build a selective amplifier with a fixed center frequency than one with a variable center frequency. Let's assume that in this example, the local oscillator frequency, FLO, is selected to be above the desired carrier frequency, FC, as shown here. Thus, the difference between the two inputs leaving the mixer is FIF. And so this signal enters the passband of the IF amplifier. Any other signals entering the mixer from the RF amplifier will not be mixed onto the IF frequency. All other signals entering the mixer will be mixed to a frequency outside of the IF passband. Let's say we want to receive a station at 980 kilohertz. The station comes in through the RF amplifier into the mixer on that frequency. The receiver is designed with an IF amplifier frequency of 455 kilohertz, a common choice for an AM IF frequency. We also assume that the local oscillator will be tuned above the carrier frequency, or FLO is greater than FC. Thus, as shown, the local oscillator must be at 980 kilohertz plus 455 kilohertz, or 1435 kilohertz. This signal will then land in the IF passband and be sent through to the demodulator. Note that FLO minus FC is exactly FIF, or 455 kilohertz, and so that is the only station in the IF passband. In the previous slide, we saw that when 980 kilohertz enters the mixer and mixes with the 1435 kilohertz local oscillator, it produced the desired 455 kilohertz IF frequency. However, will any other frequencies enter the mixer with this local oscillator and also produce the IF frequency? If so, we would have a second signal in the IF passband as shown in purple on the transfer curve. From the frequencies shown, we see that both 980 kilohertz and 1890 kilohertz can mix with 1435 kilohertz, the local oscillator, and produce 455 kilohertz from both stations. So both stations, that is the one at 980 and the one at 1890, if there is one, will mix and send a station passing through the IF passband. If there is a station at 1890, this would cause interference, since the stations would appear right on top of each other. This is an undesirable effect of the superheterodyne receiver, and it is referred to as the image frequency. Note the calculations here showing how both of these frequencies, along with the 1435 kilohertz local oscillator, lead to the 455 kilohertz IF. This slide shows the two cases of image frequencies. If FLO is above FC, we have case 1. In that case, the image will be 2 times FIF above FC. Thus, if there is a station on that frequency, it may interfere with the intended station. Similarly, if FLO is below FC, we have case 2. In that case, the image will be 2 times FIF below FC. Again, if there is a station on that frequency, it may interfere with the intended station. In order to reduce the problem of image frequencies, a common practice is to keep the bandwidth of the RF amplifier to less than 4 FIF so that the image frequencies are attended by the original RF amplifier and never enter the mixer. As a final example, we will go through all of the parameters of the receiver one more time. Again, we will assume that the AM receiver is designed to receive the 540 to 1600 kilohertz band, receiving one of the 10 kilohertz signals in the band. The IF frequency will be set to 455 kilohertz. First, we ask the question, what is the tunable range needed for the local oscillator? If we assume that the local oscillator, FLO, will be below the carrier frequency, then FIF must be equal to FLO minus FC, or FLO must be equal to FIF plus FC. Thus, over the range of the carrier frequencies, the local oscillator must tune from 995 to 2055 kilohertz. Now let's repeat the previous calculation, but this time assume that the local oscillator frequency will be below the carrier. Either design is possible. The IF frequency will still remain at 455 kilohertz. Now, FIF must be equal to FC minus FLO, or FLO must be equal to FC minus FIF. Thus, the range of the local oscillator must go from 85 kilohertz to 1145 kilohertz. Note that in both cases, the local oscillator just covers a range of 1060 kilohertz. However, in the first case, the range extended from 995 to 2055 kilohertz, just double the frequency. In the second case shown here, the range goes from 85 to 1145 kilohertz. Thus, the oscillator tuning range must increase by a factor of 12. That's a large range for a tunable oscillator to traverse, making the first approach the better receiver design, even though in theory they would work the same. With the design selected, we know that the image frequencies will be 2 times FIF above the carrier. Thus, over the AM band, we will have image frequencies from 1450 kilohertz to 2510 kilohertz. Since some of these frequencies are within the AM broadcast band, we do not want them to appear in the IF amplifier, or they will produce interfering signals in the demodulator. The approach that we have discussed is to make sure that the RF amplifier has a bandwidth less than 4 times FIF, or less than 1820 kilohertz. This would stop the image frequencies from entering the mixer in the first place, and so no interfering or image signals would be produced. This concludes the discussion of superheterodyne receivers. Homework 6, problems 1 through 5, address the superheterodyne receiver and will give you a chance to practice some of this. Before moving on to the next lecture, give them a try.